the average case efficiency of binary search. Last time we find the formula, right? The worst case formula, 2 formulas. Yeah. All right. Now let's work on the average case. All right. Yeah. So here, before we start the average case, I want to ask you one question. Yeah. All right. First, when we first let's compare the best case and the worst case. Yeah. So the best case, the number of comparisons, the number of comparisons for the best case equals 1. Right? Yeah. Yeah. When you compare the given key with the median, oh yeah, last time one student asked me about the median. So here, when I mention the median, yeah, because there is one question about the definition of the median. So let me explain a little bit. Yeah, you may have the question. Because based on our understanding, so the median should be the element right in the middle when the array is sorted, right? Yeah. So, but that understanding, there are 2 cases we need to consider. Yeah. The first case, the n, the number of elements, is an even number. The second case, the number of elements is an odd number. Right? Yeah. So for the odd case, the median, there is no confusion, right? So the element right in the middle, no confusion. Yeah. But for the even case, there are 2 elements. So if we look at the position, there are 2 elements in the middle with the similar situation, right? Yeah, equally close to the middle. Yeah. So then the question, which one should we use as the real median? Because we can only use one of the 2. Yeah, good question. All right. So one student told me the average of the 2. All right. Yeah. So let me clarify. Yeah. Because people use different ways to define the median. That's one of the definition. The average of those 2 candidates of the median. Yeah. All right. Yeah. So probably one I call M1, the other I call M2. Yeah. So one possible definition, yeah, that is the average of M1 plus M2. But there are other possible definitions, right? Yeah. Other possible definition, we just use one of the 2 candidates, right? Yeah. So M1 or M2. One of the 2. Okay? All right? Yeah. That's also some reasonable definition, right? Yeah. Now let me tell you. The first one that people use in math. Okay? Use in math. Math people use the first definition. Okay? The second one, our CS people will use the second one. Okay? All right. There is some good reason. Yeah. Because for us, if we use definition 1, we will have some trouble. We will have problem. So it's not good for us. Because this element, it is not in the array. Right? Yeah? Average of the values of 2 elements, in general, it won't be in the array, right? Yeah? Yeah. Or we can say it never, right? Never. Yeah, because sorted in ascending. Only when these 2 elements are the same, then probably in the array, right? Yeah. So in that very special case. It could be in the array. But in general, it won't be in the array. If it's not in the array, for most of our algorithms, we cannot use this median element. Yeah. So we need to pick the second one. But second one of the two, there is some uncertainty there, right? Yeah. Because some people may pick M1. Some other people may pick M2. Then people don't like that way. Yeah. So people want certainty. Yeah. In order to get certainty, M1 default median. Okay? Yeah. M1 we call the left median. M2 right median. Okay? Yeah. But the left median is the default median. Yeah. If we do not specify M left or right, then we always use the left median as our default median. Yeah. So that's the understanding of this concept. All right. Now, the best case one comparison, right? Yeah. The worst case W, we have two formulas, right? Yeah. One ceiling function log base 2 of n plus 1. The other same value but expression is different. Floor function log base 2 of n. Yeah. All right. Now the question. Yeah, because now we want to target the average case and average case. Yeah. Before we start, I want to ask you one question. Can we just write this average case efficiency number as 1/2 of best case and the worst case? Yeah, that question. Yeah, we just take average 1/2 of MB plus NW. Yeah. Think about that question. Yeah. All right. The answer is no. Yeah. The answer is no. It's not that simple. The answer is no. Not that simple. So if you calculate in this way, yeah, most of time you get a wrong answer. Wrong answer. Okay? Yeah. So why? Because the distribution of the cases is not as a linear function. Okay? Yeah? Because we know when we calculate the average case efficiency, we need to factor in all the possible cases, right? For all the possible cases, when we factor all of them in our average case efficiency, we need to consider the distribution of the cases. Okay? Right. Because for some of the cases, you need one comparison. That's the best case. Then, for some of the cases, you need two comparisons. There are a few two comparison cases. Then, there are some other three comparison cases, and so on. Okay? Yeah. All those possibilities you need to factor in. Yeah. But the distribution of those cases is not a linear function. So linear function we know, so we can draw a line like this. Okay? The distribution of one comparison, yeah, on this line. Two comparisons, yeah, on the same line. Okay? Three comparisons on the line. This kind of distribution, K comparison here, yeah, then we can apply this formula. Yeah. This formula is for the linear case. Linear case. But our binary search, it's not a linear case. Okay? So our binary search, So if you look at the curve, so it's in a curve like that. Okay, yeah, right, yeah, the curve. Oh. Yeah. So 1, 2, 3, increasing faster than that linear function. Then we cannot use. Yeah, much faster, right? Yeah, yeah. So we need to do more work to calculate the average case efficiency. More work. All right. Next. Now let's do the work. All right. Yeah. So when we do it, I like to use a simple example to get an idea. Okay. N equals 7. Yeah. Yeah. Because it's good enough. Good enough for us to understand the details of the computation process. This 7 has another property. Yeah, this 7 number, I pick a special number, yeah, very friendly for our calculation. Because this 7 is a number power of 2 minus 1, 2 to the third minus 1. Yeah. So this special number corresponds to a special structure for our binary search. Yeah. So when we draw a binary tree corresponds to our binary search, we will get a complete binary tree. Yeah. So this special number corresponds to a complete. So try to recall the meaning. Complete binary tree. Okay? Yeah. Why? So what's the meaning complete? All the levels are full. Okay? Yeah. When you draw a binary tree, yeah, you have many levels, right? So all the levels are full. Yeah. So we will see that quickly. Yeah. All right. So now let's do the calculation work. All right. We have 7 positions in a binary, in a given array. Yeah. Then, so this black dot, given key. So we do comparison. All right. The first comparison, we compare V with node 4. Yeah. All right? Yeah. Yeah. Here, yeah, we need to make a simple assumption. We assume, yeah, V is in the array. Yeah. If V is not in the array, then we can use probability P. Yeah. But here we don't want to go that direction. Yeah. Yeah. So we know how to handle it. In our module 1, when we do the linear search, we use the probability P way. Yeah. So here I do not repeat it. Yeah. All right. Now the first comparison, compare V with node 4. So we put the node 4 as the root node of our binary tree. Yeah. So the first one, yeah, at the root, yeah, root node. Yeah. All right. Then we need a 1 comparison. So I put this 1 here. Yeah. All right. Then after that, there are 2 branches. We can go, yeah, left branch, right branch. Yeah. For the left branch, the next round comparison, we should compare V with 2 for the left branch. Right branch, we should compare V with 6, node 6. Yeah. So, yeah. So that's the level with comparison number 2. Right? Yeah. And so on. Yeah. So another round, then node 1, node 3, yeah, left branch, right branch, and also node 5, node 7. This level, we need to do 3 comparisons. that corresponds to the worst case efficiency. See? Yeah. So there are 3 levels in this binary tree. And also you can see this is a complete binary tree. Yeah. Because all the levels are full, right? Yeah. All the levels are full. Okay? Yeah. Yeah. You cannot insert any new node in any level. Okay? Yeah. All the positions are occupied. Yeah. Yeah. For each level. Yeah. Then now we are ready. So with this diagram, now we are ready to calculate the average case efficiency. Yeah. All right. To calculate that, yeah, look at the formula. The average, if you first, the denominator, because there are 7 nodes, so the total number of nodes we put at the denominator. Then the numerator, we need to count the total number of comparisons for all the cases. Yeah. For case 1, yeah, so each node has 1 comparison, but we have only 1 such node. So that's why 1 times 1. Yeah? For the top level. Okay? For the next level, each node, we need to do 2 comparisons, but we have total 2 such nodes in that level, so we do 2 times 2. Yeah. All right? Yeah. Accumulate all the comparison numbers for all the cases. Yeah. The bottom level, each node, we need to do 3 comparisons. But we have total 4 such nodes. So the subtotal number 3 times 4. Yeah. Yeah. The first number you can see the number of comparisons, right? Yeah. So when you write, yeah, because later you need to calculate n for certain given number, right? Yeah. So when you do the calculation, yeah, in our homework assignment number 2, you will have 1 question like this. Yeah. So you will see, yeah, so this number means number of comparisons. Yeah. For each node in this level. That one, yeah, so let me call the subtotal number of nodes in this level. Okay? Yeah. Yeah, yeah. So then we can find the average case efficiency. Then for this question, the answer is 17/7. Yeah. Yeah. Final answer. So this is the accurate number for this answer. Yeah. But here I want to point out one common error in your homework, in the previous students. Yeah, point out the error. The error is many students, yeah, so they understand the average case efficiency in a wrong way. So what's that? Yeah. So their logic is like this. Because here we want to count the number of comparisons. So then they feel the answer should be an integer, because number of comparisons should be an integer. Then after they get the answer, they round it to closest integer. All right? Yeah. So many students did that way. So here I want to say it's wrong. Yeah. Because the average, although the number comparison should be integer number, but when we do the average of a set of integer numbers, we don't have to get integer number, right? Yeah. Average of certain integer numbers, we do not need to require. We do not have to require the answer must be also integer, right? Yeah. So the average case. So best case, worst case must be integers. Yeah. So we have no question. Yeah. Best case, worst case. But the average case do not need to be an integer. Yeah. Yeah. Just leave this fraction number as your final answer. Otherwise, if you round it up or round it down, you will lose some point. Okay? Yeah. Yeah. Because conceptually it is wrong. Yeah. Conceptually it is wrong. Yeah. All right. Yeah. So we complete this topic. Yeah. Okay? Yeah. So that's the way we calculate the average case efficiency. Yeah. All right. Next topic. Yeah. Introduction to selection problem. So we need to look at the general selection problem. So we did a very special selection problem. Find the maximum, find the minimum, right? Find both the maximum and the minimum. Yeah. So we solved those special selection problems before, but this time we want to consider the general selection problem. Yeah. So given an array and a positive integer k, yeah. All right. We want to find the kth smallest element in this array. Yeah. This is the general selection problem. Yeah. Yeah. So here, yeah. So some people call this kth order statistic of this array. Kth order statistic. Order number. Statistic. All right? Yeah. And another terminology people use for this k number, that's the rank. Yeah. The rank equals k. Yeah. Yeah. So rank equals 1, 2, 3, and so on. All right. Now let's look at this general. We do some analysis for this general problem. Yeah, the first one, the data is unordered. Yeah. So the given array. Yeah. So we assume it is unordered. Yeah. Then the question. Yeah, because some people may like to do the sorting first. Sort the array. Then, for any k, you can select easily, right? Yeah. So, yeah. All right. So here I want to make some comments on this way. Yeah. All right. Because we know when we do the sorting, the number of comparisons we need is big theta of n log n. Next, in our part C, part D, so we will study n log n sorting algorithms. At this point, we have not learned n log n sorting algorithms. Yeah. All right. So this is a little too much. Yeah. If we need to pay this much, that's not the most efficient way to solve this problem. No, so n log n. Yeah. All right. Yeah. So the reason is if you only need to find one kth order statistic, an element with kth order statistic, you do not need to sort it. So you do more than necessary comparison work than necessary. Yeah, right? Yeah. 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 So here we want to find the most efficient algorithm. Yeah. All right. So then the question. So to solve it in an efficient way, we need to use divide and conquer. Divide and conquer. Yeah. So for the divide and conquer, the divide step, we need to, try to find a good way to divide the given array. Yeah. To avoid those cases that may result in bad algorithms. Yeah. So that's the idea. Yeah. Yeah. So here I can tell you, so our target is a big theta of n algorithm. Remove that log n part. Yeah. Yeah. So we can, there is an algorithm that can solve the general selection problem in big theta of n. Yeah. All right. So then to do that, yeah, so we need to find a well-organized way to divide and conquer the given data. Yeah. All right. Idea here. Divide the problem into two subproblems. Yeah. Two subarrays. Yeah. All right. Then the element with kth order statistic falls in one of the two subarrays. So by elimination method, you can drop one of the two subarrays, right? Yeah, just like the binary search. Yeah. Yeah. But here, the challenging part is the array is unordered. Yeah. So it is very hard to tell which subarray contains the target element with kth order statistic. It's very hard to determine that. It's not like binary search. It's very easy to determine which of the two subarrays contain the given key. Yeah. All right. Yeah. So, then, yeah. So this first step, divide step, is very critical. Yeah. The remaining conquer, we can do recursion, right? Divide and conquer, recursion, Yeah. So the most difficult step is the divide step here. All right. Yeah. So here, so when we consider the divide step, so here, there is so let's look at the elimination idea here. There are two cases we can consider. Yeah? Because when we look at the kth order statistic, kth order statistic, then this is the kth smallest, right? Yeah, so this means kth smallest element. Yeah. Then, because this we look at from the left side, right? Yeah. But we can also look at it from the right-hand side, right? Yeah. So here, rth order statistic. So that means the same element can also be treated as rth largest element, right? Yeah. So we count it. We count the number of elements from the right side. Yeah. There are two ways. Yeah. Yeah. So we like to pick the relatively easier way. Yeah. All right. Yeah. So there are two cases: elimination from the left end, elimination from the right end. Yeah. All right. Yeah. So here, yeah, because here I want to talk about this question in the general situation. Yeah. So in this general situation, divide and conquer, yeah, we need to consider under what situation we may get bad algorithms. Under what situation, yeah, we may get bad algorithms. We need to understand that part. So we want to avoid the possible bad algorithms. Yeah. All right. Yeah. So the situation is, yeah, we consider the worst case scenario. The worst case scenario. All right. Yeah. So when you divide this line segment, if the split occurs near the end, near one of the two ends, yeah, near one of the two ends, okay, then it's not efficient. It's not efficient. Yeah, because when you do that kind of unbalanced division, so they are unbalanced division. Yeah. Then, for the worst case, so you drop the smaller subarray, right? For the worst case, you keep the larger subarray. That means in the next round, divide and conquer, you need to do more work. Okay? Yeah. Next round, you need to do more work. Yeah. So you want to avoid unbalanced division like that. Avoid that. Okay? Yeah. So based on that understanding, so when you design your device step, you should control, okay? You should control the divide point close to the middle. Yeah. Not necessarily right in the middle, yeah, because it's very hard. Yeah. If you require too much, then in the device step, you need too many comparisons. Yeah. So for that reason, so you need to do something in a balanced way. Yeah. In the device step, we don't want to do too much work, but we try to avoid the very bad unbalanced cases. Yeah. The bad unbalanced cases near two ends. Okay? Yeah. Yeah. So we want to make the division location, yeah, somewhere near the middle. That's the idea. That's the main idea of this method. Okay? Yeah. All right. Yeah. All right. So based on this understanding, yeah, so we can try to solve this problem. Yeah. All right. But how to make that happen? Yeah. It's not that easy. Yeah. Yeah. Pretty hard. Yeah. All right. Yeah. But it's doable. It can be done. It can be solved. All right. Yeah. So here, yeah, I like to yeah, at this point today, yeah, let me look at how much time I have. Yeah, yeah. Today I want to do overview first. Yeah, yeah, because later at some time, if I can find some time, so I can talk about the remaining implementation ideas. Today I want to do the overview. Yeah, yeah. Give it the result. Yeah, and talk about some related information. Overview on the selection problem. Yeah. All right. Yeah, sorry. Yeah. All right. Here. Yeah. So the goal of the method find an algorithm in big theta of n. Okay? Yeah. The idea so divide the array avoiding the unbalanced cases. All right. Yeah. So that's the main idea. Okay. All right. Yeah. All right. So then for the implementation. Yeah. So here, yeah. A little more information. Yeah. What I'm going to divide. Yeah. All right. But how do you control? How do you control this requirement? Yeah. Yeah. So you need to do something very smart. Yeah. How do you control that? Yeah. So the point, yeah, so here, the division location, all right, so more specifically, yeah. So the division location, yeah, yeah. We don't want to, yeah, so here we need to find a smart way to put the division location not very close to the end. Okay? Yeah. Yeah. So find some smart way to put the division location not very close to the two ends. That idea. Okay? Yeah. That's the control. Suitable locations. How to control suitable locations. All right. Yeah. Yes. So that algorithm, yeah, for the left end, near the left end, yeah, avoid 30%. Yeah. Yeah. Right end also 30%. Okay? All right. So avoid 30% of the elements in the left end and 30% of the elements in the right end. Yeah. Yeah. So the division position is in the 40% around the middle position. Okay? Yeah. Right. Yeah. In this way, you avoid poor performance situation. Poor performance situation. Yeah. But how to make it happen? How to make it happen? Yeah. So the algorithm is very smart. Yeah. It's relatively complicated, yeah, but it is quite smart. Yeah. 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 But today I will not get to that part because it may take too much time. Yeah. So because today we just do the overview. Yeah. Yeah. So we delay the details later sometime. Okay? We delay the details. Yeah. 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 Later sometime. Okay? All right. All right. So next, yeah, because I want to cover some more special selection problems to prepare us for our homework assignment number 2. Yeah. Yeah, let me see. So when I plan to give you homework assignment number 2. Yeah. So not this week, next week. Next week we will be ready. Yeah, because next week we will pretty much complete module 4. Yeah. Module 4. So we can work on the homework assignment number 2. Yeah. All right. Then this B.5, find the median of 5 element array. Yeah. So this is a interesting, important question. Yeah. All right. So let's solve this problem first. Yeah. Find the median of 5 element array. Yeah. Yeah. So the answer, let me give you an answer first. Answer is 6 comparisons. We need 6 comparisons to find the median of 5 element array. Okay? All right. Yeah. Another related problem, remember in part A of module 4, we have 1 question left. We haven't completed. Yeah. Sort 5 element array, that one. Yeah. So we need to complete it soon. Yeah. So that one, sorting 5 element array, this one, the optimal solution needs 7 comparisons. Okay, this is optimal. This is optimal. Okay, yeah. Yeah. How do you know optimal? Yeah, so because how do you know it's optimal? Yeah. Remember, so here I'll give you a formula. There is a formula that can tell us if it is optimal. All right. So the formula called the lower bound. Lower bound.
Is there 7 comparisons or 1 comparison?
7 comparison. 7. Yeah. Yeah. No, not 1. Yeah. Yeah. Lower bound for what? Lower bound for sorting Yeah. So this sorting, yeah, I need to put some description for this for sorting. For comparison. Comparison sorts. Okay? Yeah. Because there are some uncomparison sorts. Yeah. So there are some special sorts. They do not use comparison. Yeah. Yeah. So later, when we have time, we will study counting sort. We do counting. We do not do comparison. Okay? We can still sort. Yeah. Special sorts. Yeah. But this lower bound is for comparison-based sorts. Okay? So that lower bound is ceiling function of log base 2 of n factorial. Lower bound. Lower bound means the number of comparisons must be greater or equal to this number. It can never be less than this number. Okay? Yeah. Lower bound. It can never happen with lower than this number. Then, this lower bound, when n equals 5, we can calculate. N equals 5. 5 factorial equals 120, right? 120. Then, log base 2 of 120 ceiling function. Yeah? Because we know 2 to the 6th equals 64. 2 to the 7th equals 128. Yeah. So this 120 is between these 2 power of 2, so it should be 6 point something, right? 6 point something, that ceiling function is 7. So that means when you use comparison sorts to sort 5-element array, the minimum number of comparisons, 7 comparisons. The minimum number of, lower bound, it's lower bound. So if you can get a 7 comparison solution, it's optimal. Yeah. Because this formula tells us nobody can use 6 comparisons to sort 5-element array. Nobody can do it. Okay? 6 comparisons to sort 5. Yeah. But how to get this formula? Yeah, later, when I have time, I will show you the idea. The idea is very interesting. Yeah. So a lot of useful analysis method we can learn from derivation of this formula. Yeah. So I hope we have time. Yeah, because this semester actually we will have plenty of time. Yeah. All right. Now next, let's work on this B.5 question. Yeah. All right. So the question, find the median of a 5-element array. Okay, yeah. So this one, because this result is very important. Yeah, remember, we use some notations to order useful results for our final, right? Yeah. So we did 4 before. Okay. All right. So this is the 5th one. Final basic result. Okay. Yeah. So final basic result number 5. This one is. Yeah. Sort 5-element array. That's number 4. Yeah. So we need to complete that number 4 one. All right. Yeah. Solution. Yeah. So here we apply the tournament method. Yeah. So the goal, 6 comparisons. That's our goal. Okay, all right. So we apply the tournament method. Yeah. Yeah. So we are familiar with this. Okay. Yeah. Here we use X. Yeah, our data. 5 elements. X1, X2. X3, X4, X5. All right, yeah. The first round, tournament method, X1, X2, X3, X4, power of 2, yeah. So the 5th element, we leave it out for the first round. Yeah, because this is just the first round. Okay? Yeah. So we leave it out. Okay. All right. Then, comparison number 1 between X1 and X2, a winner. Yeah, so first comparison, the winner, let's assume X1 is the winner. Yeah. Without loss of generality. Yeah. And the second comparison, we can assume X3 is the winner. All right. Then, third comparison between 2 winners. That's our third comparison. Let's assume X1 is the winner. Okay? Yeah. After that, then let's do some cleanup work, or we do some summary work. Okay? Yeah. So now our data becomes, so we need to organize our data. Yeah. Based on the known information, we arrange our data based on known information. Yeah. So we use diagram. Yeah. So diagram. All right. X1 higher, greater, yeah. Then X3, X4. Yeah. In this order. Okay? So we can order the chain. This is a 3-element ordered chain. Okay? But there is another one, X2, below X1. Yeah. So X2 is here. Okay? Yeah. Yeah. And X5, unknown, right? We have no information about X5. Okay, all right. So next question. We need to apply the elimination method. Next round, the second round. Yeah. Elimination method. Apply elimination method. So which element has no chance to be the median, we can eliminate it from the consideration. Which one has no chance to be the median? Yeah. So we need to describe the median. So we need to describe the median here. Yeah. Be careful. Yeah, be careful. Yeah. So let me describe the median. Then you answer this question again. Okay? All right. Median, there are 2 ways to describe this median. The first way, third largest element, right? Is median the third largest element? Yeah. Second way, describe third smallest element, right? That's the median. Okay? Based on this understanding, so either third largest or third smallest, now you answer the question, which element has no chance to be the median? Cannot be the third largest or third smallest. If one is true, we can eliminate. X4, is it smaller than X2? Yeah. We don't know, right? X4 and X2, which one is larger, which one is smaller? Unknown. Then you cannot say anything. Yeah. How about X1? Why you ignore X1? Greater than at least the 3 elements, right? That's for sure. Okay? So can we say X1 cannot be the third smallest element? Because you find at least 3. That's absolutely less than X1, right? Yeah. So the one that we can eliminate it because it cannot be the third smallest element. Yeah. Okay? So now, this step is important. Yeah. This elimination step is important. Yeah. 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 So why? Here, let me explain why this step is critical. Yeah. Yeah. For this problem-solving question, this step is critical. Yeah. Because when you give this question to most people, yeah, the hardest step to, break through is this step. Okay, all right. Yeah, because most people, they do not realize they can eliminate X1 in this step. They do not realize it. Yeah. If you do not realize you can eliminate X1, the consequence is the X1, this element, it is unrelated to the median, but there is a chance it may join the comparison, right? It may join your future comparisons, then it's a redundant comparison. When you do any comparison related to X1, you throw it away. You throw your resource away. You waste your resource. So that's why we need to remove it. Yeah. All right. After this step, yeah. Now, cleanup work. we have four elements left. Yeah. So we need to, clean up a little bit. Yeah. So our current situation. All right. 2 elements in order, X3, X4. Then, but there are 2 other elements, X2 and X5. Yeah. So we don't have any information, right? Yeah. After elimination, so we start a new round. Yeah. Start a new round. Yeah. So here, so we can. So here, let me do. So the first round, so this is the round 1. Round 1, okay? This is round 2. This elimination step, that is the round 2. So now, this part, okay? Round 3. All right, yeah. So in this round 3, we need to adjust our goal, right? Yeah. So we need to adjust our goal. Yeah. Yeah. Our goal, because our goal is find the original median, right? Original median.
You wrote x2 is
Yes. We need to update the rank for the original median. Original median becomes, because we remove x1, becomes second largest, right? Second largest element. Second largest in these four elements, x2, x3, x4, 4, and x5. Yeah? Yeah. Yeah? Because x1 is among top two. Yeah, among top two. We eliminate it. Then we come from top. So our original median must be the second largest. Okay? So before this round, it is third largest, but the one in the top two is removed. So then the previous third largest becomes the current second largest. How about that? Okay? All right. Now, to find the second largest element in 4-element array, we know how to do it, right? Yeah. 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 So we have the experience in our homework assignment 1. So we did this kind of thing, quite a lot. Okay? All right. So then our comparison number 4 between x2 and x5. So this is comparison number 4. Okay? Yeah, sorry. Oh, this is 4. Yeah, not 2. Yeah, all right? All right. Then the 5th comparison between the two winners. Okay? Yeah. Yeah. Two winner, no matter which one, so the 5th one. The winner, so you can assume x2 the winner, okay? Yeah, because symmetric. Yeah. When we have two symmetric cases, we just pick any one. Any one of the two symmetric cases. Yeah. So here, it's a symmetric situation. Yeah. Symmetry situation. Yeah. So the 5th, the largest. Then the last comparison, direct loser of the winner. Winner is x2. Direct loser of x2, that's x5 and x3. That's direct loser. So the last comparison, the 6th comparison between direct loser of x5 and x3. So then the final conclusion, the winner of x3 and x5, what are they? So here, because this view, so they are direct losers of x2. Okay? Yeah. So the winner is the solution. Yeah. Solution that is original median, right? Yeah. So what do you mean solution? Original median. Now you can see 6 comparisons. Yeah. 6 comparisons. Yeah. And here you can see, we use 3 rounds of comparisons. 3 rounds. Yeah. All right. Yeah, actually, second round, we just do elimination, right? Yeah, we didn't do comparison in the second round. Yeah. But we do a critical operation, that's the elimination. Yeah. It's critical for this problem solving. Yeah. So although we do not do any comparison. Yeah. All right. So then, think about. Yeah. Yeah, because this is a very challenging question. Yeah. So if you give this question to your friends working in IT industry, yeah, it is very challenging. Yeah. Because usually they may not have the background that we have. Yeah. So we have the background about the tournament method, elimination method, right? Find the second largest, that kind of background. So they may not have. Yeah. So if you have some good friends working in IT industry, yeah, so you can let them try. Usually it's several hours work. Yeah. If they can solve in several hours, well, so that's already very good. Yeah, this question. Yeah. All right. Yeah. Then, this question, very useful, very important. Now, after you know how to find the median of 5-element array, very useful. Remember, in the previous topic, I talked about solving the general selection problem. That problem, we do division, try to avoid unbalanced case, right? How to do that? We need to use the result of this question. Yeah, we need to apply this one. See, very useful. Yeah, so, yeah. I will find time later, so we apply the result of this question. We will find a smart way to make our division away from the two ends. Okay, 30%. Yeah, that 30% distance away from the two ends. Yeah, using this method. So very smart. Yeah. All right, so that's it. Yeah, and just remind you again. This weekend I will post our. Not this weekend, sorry. But this weekend I will post the quiz. Quiz number 4. Okay? Yeah. Quiz number 4. Yeah. Covering, because module 3 we need to practice a little bit. So then module 4, part A, part B. So module 3, part C, part D, right? Yeah, for example, part C, part D of module 3 and part A, part B of module 4. So we need to do quiz number 4. Yeah. So next week we need to do homework assignment number 2. Yeah. All right, that's it.